Koji, and I think it's time for the next speaker, Alex Rice, speaking about new minimal linear inferences in Boolean logic, independent on switch and medial. Sorry.
Okay, can you see my slides?
I think this will be a live talk, is it? Or pre-recorded? Anyway, go on, Alex.
Can you see my slides and hear me?
Sure, I can see.
Okay, so I'd like to start by thanking everyone who's helped organise FSCD this year and put work into making this actually happen. Yeah, today I'm going to talk to you about joint work I did with Anupam, who's actually talking in an hour about linear inferences in Boolean logic, and I'm going to explain what all these terms mean for the talk, present the problem we tackled, and then present how we solved it and what we found along the way. So here we go. So yeah, this is an outline of the talk, which I kind of just gave, but just to give it more detail, I'm going to start by talking about what linear inferences are, and then I'm going to move on to, so at the end of that section, I'll explain what the problem we wanted to tackle was. After that, I'll explain what relation webs are, which is a key tool we used in our solution. And it'll become clear how these help us. In the second section, I will present an algorithm that we made to solve this problem and also briefly discuss an implementation we made of this algorithm. And then finally, I will go over the results that we got from this. So in this talk, we're going to consider standard propositional formulae with connectives and an or, and we're going to have constants top and bottom, and we're going to allow negation of variables with the idea that this really represents the whole of propositional logic as up to De Morgan's laws. So we can just push any negation down to all the variables. And then we're going to call a linear formula is a formula where each variable only appears at most once. So I just want to make the distinction clear at this point that we're not considering, we're not talking about linear logic or anything where we don't have these structural rules. We're just talking about a subset of propositional logic. Oh, that's one way. And then a linear inference is going to be a valid implication phi to psi, where phi and psi are themselves linear formulae. And we don't put any condition that these phi and psi have to have the same variables. We're just saying that both of them have to be linear. And then so a natural question to ask might be, well, is this subset of propositional logic actually interesting? Is there any sort of difficulty in it? And the answer is yes. In fact, this the set of linear inferences is co-MP complete. So it really has the same level of complexity as the full tautology problem. Also, these linear inferences form the multiplicative fragment of Blass's game semantics for linear logic. So they're seen in other places as well, and they've been studied a lot in the literature before. So moving on, in this talk, we're mainly going, as the title would suggest, we're mainly looking at these two linear inferences, switch and medial. So firstly, we can see that these are examples of linear inferences. So the left and right hand side only contain each variable at most once. These two do have the same variables on each side, but as I said before, this isn't necessary. We have the switch is important because it underlies multiplicative linear logic, and medial is important as together with switch, it forms the logical fragment of deep inference proof theory. Medial also allows locality of contraction, which means, so if we have something like phi or phi implies phi, then using medial, we can reduce a proof of this to just contraction of single variables. But if that doesn't mean anything, then it's not going to affect the rest of the talk. So don't worry. If that example meant something to you, then great. Otherwise, it's not a problem. So the next thing we do is that we want to be able to compose these inferences and get more complicated and bigger ones. And it's just in general a nice thing to be able to take larger linear inferences and say these can be built up by these smaller parts, such as the switch and medial we presented before. And to do this, we're going to use rewriting, which I think a lot of people in this conference will have seen before, but I'm going to go through it anyway. So just to give an example for me rewriting with switch and medial, what we're going to do is we're going to take our formulae and we're effectively going to take out the premise of whatever we're rewriting by and paste in the conclusion. So in this first bit, we've rewritten by a switch. So we've identified this lines up with the premise of switch, and we've replaced this by the conclusion here. Next, we could do another switch rewrite. This time, notice that we're allowed to manipulate whole subformulas. So we're taking this x and y as one block. And then lastly, we can apply a medial like this. And so you may notice that when giving this example, I've not been particularly strict about associativity and commutativity. So in particular, I didn't put any brackets on this first one. And so we're going to have to be more careful about this from now on. So to get around this, I'm going to introduce this relation. So this relation is going to be the smallest congruence that containing associativity, commutativity, and unit laws. So these are these top ones are the associativity and commutativity. So both the or connective and the and connective are commutative given by these two and associative given by these two here. And we also have these unit laws here, which say that top is the unit for and, bottom is the unit for or, and they're cancellation with the other connective. Now we can actually give a definition to our rewriting relationship. So we're going to say that this single arrow is the term rewrite system. So this is just what I said earlier of taking your formula, taking out the premise and putting in the conclusion. And what we're going to do is pad this out by this congruence. So this squiggly arrow is going to mean that there are some linear formula phi prime and psi prime. And then what we're going to do is we're going to go from phi, we can rearrange the associativity and commutative and units however we want to get to phi prime. Then we apply either our medial or switch rewrite to get to psi prime. And then again, we can apply whatever associativity and commutativity and units we wanted to. And what we're really going to think about is the reflexive transitive closure of this relationship. And so the natural question that comes up now is we've got this way of composing inferences and we've got these two inferences we've looked at. And so at least the question that I think of is what class of inferences do we get when we consider all the things that are derivable from these two? And this is a question that's been thought about for a while now. So yeah, the question is basically what class do we get from this switch and medial? And so there's some existing results here. So firstly, we know that all 6 variable linear inferences, so this is 6 linear inferences that contain 6 variables or fewer. We know that they are all derivable from switch and medial. And this was done by a computational search. Unfortunately, in this here, computational limits were reached at 7 variables, and we're going to go over what exactly sort of happened that held this back in a way. We also know that assuming a less co-MP equals MP, then the set of linear inferences cannot have a polynomial time basis. So in particular, this would imply that it doesn't have any finite basis. So this suggests that switch and medial do not derive all inferences. And in fact, even before this result was found, a 36 variable linear inference that could not be derived was found by Strasburger. And this, so this inference was generated by an instance of the pigeonhole principle. And yeah, so then later on, my co-author Anupam found a 10 variable inference, which again is derived from the pigeonhole principle, but this time with fewer pigeons and fewer holes. And this is also not derivable by switch and medial. And so hopefully you can see that this leaves a sort of gap in the knowledge, as we know there's a 10 variable one which cannot be derived, and we know all the 6 variable ones can be derived. So the natural question is, what's the smallest inference that we cannot derive with switch and medial? And this is the question that we've tackled in our work. So as I sort of said just a bit ago, the main problem with the computational search here was that it just ran into sort of algorithmic limits at 7 variables. And part of the reason this happened was it was working with the actual syntactic formulae, and it had to consider all these associativity and commutativity relationships that I went through before. And this massively increases the search space of what we're looking at. And so I think our main improvement from this work has been to leverage the idea of relation webs, which I'll go into now. So before I get too much into relation webs, I'm just going to say it turns out that it's sufficient to consider constant free, so unit free, and negation free formulae. Unfortunately, I don't really have time to go into why this is the case in this talk. There's a lot more detail in the paper of this, why this is the case, but the basic idea is that anything that contains, or any inference that is not semantically trivial, we can remove all the negation and constants from it. And if it is semantically trivial, we can reduce it to a smaller formula, and we can sort everything out that way. So yeah, so unfortunately for this talk, I'm just going to have to claim that this is the case and move on. But then once we have these constant-free, negation-free formulae, what we can do is we can represent them by relation webs. And what this does is it effectively quotients out by the associativity. So I should say that we don't really have these unitality relations anymore because we're considering constant-free formulae. And then these relation webs give us a way to quotient out by the remaining associativity and commutativity. So a relation web is just an undirected graph which is P4 free, which means none of its induced subgraphs are isomorphic to this graph here, which is P4. So in this graph, I've drawn edges by these red edges here, and I've drawn the lack of an edge by these green dotted lines. So so I think what you might be thinking is, well, what does this graph have to do with these formulae I said above? And the answer is that every formula can be translated into one of these graphs. So from a formula, we can generate a web as follows. We have the nodes of the graph are just the variables of phi. And then we say there's an edge between x and y if the smallest subformula containing x and y has an and as it at the top of it. So maybe this will be clearer with an example. So if we take this rewrite we looked at earlier, so let's say we look at this right-hand one. So we've got the nodes of our graph are w, x, y, and z, just as the variables of this formula. And then if we look at, for example, w and x, the smallest subformula containing these is just this w or x. So this has an or as its topmost connective. So this doesn't have an edge. And then, for example, w and z, the smallest subformula containing both of them is the whole formula, which contains an and at the top. So this does have an edge. And we can continue constructing this in this way. And the key idea here is that, as you can see, again, I haven't written these brackets. So we could have bracketed this as w and x and y and z, or we could have bracketed it this way. And it doesn't matter for these relation webs. We would have got the same graph out no matter which way we bracketed this. And so this is exactly what we want. We have a representation of the formulae which doesn't care about how we bracket it. And moreover, we actually have a way to check if inferences are valid just using these graphs. So it turns out if we know the maximum clique data, all the maximum cliques of 2 graphs, we can determine whether the inferences are valid. So what this means is now we only have to work with graphs, and we can just forget about the formulae completely. which makes everything a lot simpler. So now I can get onto our algorithm that we made to search for these linear inferences and determine whether they're derivable. And I should add that we wrote an implementation that's which capable of running the algorithm, and it was able to run up to 8 variables. So before I get to the results, I'm just going to go through a quick sketch of how this algorithm works. So the algorithm takes in a natural number, which is going to be the, so if say we take in the natural number 7, we're going to look for 7 variable inferences to check if they're derivable, for example. So say we've got this number n, then the first thing we do is we generate a list of all the P43 graphs of that size. And even this can start to run into computational limits, because if we think about the n equals 7 case, which was sort of the first case we were tackling, then if we think about this, then there are something like 2 to the 21 different total graphs. And if we want to check whether all of these are P43, that's a lot of computation, as we have to check every single subgraph of size 4. So doing this naively of just generate everything and then check if they're P43 doesn't really work. Luckily, we were able to leverage the fact that a subgraph or an induced subgraph of a P43 graph is itself P43. And so we can use a recursive algorithm to generate all of these. Once we've done these, we identified isomorphism classes of these graphs. So the idea here is that if we have an inference and we apply the same isomorphism to both sides, we get another inference which is equivalid and equiderivable. So we can sort of factor out by one set of isomorphisms. After this, we found the maximal clique data of all the graphs we had. And yeah, this didn't run into any problems. And as I said before, this gives us the machinery to check if inferences are valid. And so after this step, we needed to check that we needed to filter out all our inferences and check which ones were left, which I've said here. Okay, so the next part was to check each pair formula for inferences. And as I sort of hinted at before, this isomorphism part, it's sufficient to check these pairs where the first one is a canonical representative of the isomorphism class. Next is potentially the most important part. We restrict to logically minimal inferences. So what this means is that if we've got, so an inference is logically minimal if there's no distinct interpolating formula. So if we've got phi to psi, we say this is minimal if whenever we've got phi to chi and chi to psi being valid, then chi was equivalent to either phi or psi. So effectively, these are the smallest building blocks in our system. And this has 2 benefits. So the first benefit is we again reduce the search space of the inferences that we need to check. And the second benefit, which is probably the most important one, is that each remaining inference is either a single application of switch or medial, or it's not derivable at all. So just to see this, if it was derivable but wasn't a single application, then it would be a case of multiple rewrites by switch and medial, but then it wouldn't be logically minimal. And then lastly, as we only have to check whether each thing left is a single instance of switch or medial, we can just check whatever's left. And this turns out to be perfectly doable. So now I can get on to the results we got to. So we ran our algorithm on 7 variables, and it found that every 7 variable inference is derivable from switch and medial. And then further, our algorithm turned out to be fast enough to also run on 8 variables, and we found 2 minimal underivable inferences. And so this answers the question from before, that the smallest inference that is not derivable from switch and medial has 8 variables. And this was originally what we were aiming for. We wanted to answer this question, but it turns out we actually found a bit more while we were doing this. So this was sort of where we were trying to get to, but then it turned out there was also something interesting about the inferences we found. So this one at the top is, the algorithm found both these inferences. The one at the top was actually found independently of the implementation by my co-author by simplifying the 10 variable inference he had before. So in a way, this one is still derived from this pigeonhole principle. However, the second one is completely new, and I've drawn its graph out here, and it has this interesting property that it contradicts a previous conjecture that was made. So what this conjecture said is that in any one of these sort of minimal inferences in this style, then either all the red edges to be sent to red edges, or all the green edges should be sent to green edges. So I think switch satisfies one of these conditions and medial satisfies the other. I can't remember which way around they are off the top of my head. But in this graph, we can see that this edge y prime to z prime goes from green to red, and there are loads of edges everywhere that go from red to green. And so what this means is that this conjecture was made because everything that comes from one of these combinatorial principles would satisfy this conjecture. So in a way, the new inference we found, it can't come from one of these combinatorial principles, and we sort of claim that it really only could have been found by computational search, because, or at least not with, we don't think it could have been found with the tools we currently know. So we thought that was sort of an interesting bonus we got at the end of this search, as well as answering the question that was open. We found this interesting inference. So yeah, just, I think, coming to the end of the talk. So just to conclude everything. So we made an implementation. So we made an implementation to search for linear inferences for derivability. And we crucially used these graph theoretic tools to reduce our search space and make the problem actually tackleable. And it's something that I haven't talked about much, but it's worth noting that the implementation we made is written in a generic way, which can be applied to anything using these relation webs, and this includes some further work that's happened recently, where these graphs are treated as first-class objects of the logic, and I've added a few references in there if anyone wants to check out that work. And then we ourselves use this implementation to implement our algorithm that solved an open problem of the size of the smallest inference that was underivable from switch and medial. And then, as a bonus, we were further able to classify the 8 variable inferences, including this one on the previous slide that contradicts a previous conjecture. So yeah, thank you all for listening, and I'd welcome any questions.
So let us thank the speaker. And any questions? You may write by chat, or you may raise your hand. I will, as soon as you stop giving your presentation, I may look to the...
Oh, so I stop sharing then?
Yeah, you should stop sharing the...
Okay.
Otherwise, I cannot see the raised hands. So, any questions? So maybe you want to add something to Alex while people are thinking to the question. We have still 5 minutes before the next talk, so no problem.
I think I said everything I really wanted to, in a way.
What?
I think I said everything I wanted to get through, in a way. Yeah, I don't know what I can add to what I've said.
So you may put again your... you may put again your last slide.
Okay, I'll add that. No, I can't see anything. I've also added in some references at the end, which I think if anyone wants the slides, they can have them.
By linear inference, sorry, what a stupid question. You mean no duplications, or there is some other meaning for linear?
So if I go right back to the start, all we meant by a linear inference is
it's a linear
inference. It's an inference that is valid in completely regular propositional logic, but with this extra syntactic condition that each of the premise and conclusion were themselves only had each variable once. That was the only that was the only condition we meant by linear inference.
Okay.
Maybe I could add that sort of a natural question that's been asked before might be that, well, like we said, this implementation ran up to 8 variables. One possible question is, can we do 9? And the problem sort of breaks down at this point because our implementation is only considering whether things are switch medial derivable, and really for 9 variables, we would want to say, are they switch medial plus these 2 derivable? And so,
not derivable, you mean that you may derive it if you add the what?
By derivable, I mean we can generate the inference by rewriting with those rules. That's what I mean by derivable. And maybe another thing to add is that if anyone sort of knows anything about this inference here, because we know nothing about it, it just came up as this counterexample, but it's potentially interesting somewhere, but we don't know where. So if anyone has seen it before or recognizes anything about it, then we'd be happy to know.
Okay, so let us thank the speaker again, and in 2 minutes, in 1 minute actually, we will start the next talk. So thank you. I will know how to clap, I hope, before the end of the session. Okay, in 1 minute, we will have the new talk by Daniel Méry.